Welcome all to this new session, which is going to discuss the kinetics of particles, force and acceleration. We're going to consider three sections, talking about Newton's second law of motion, the equation of motion, and the motion of a system particles. So the main objective of this session is to introduce the Newton's law of motion. As we discussed in chapter number 12, the kinetics part of dynamics deal with the forces that causes the motion. So the motion of an object depends on the forces acting on it. A parachutist relies on the atmospheric drag resistance force to limit his velocity. So Newton has three laws of motion. The first law states that the particle originally at rest or moving in a straight line at a constant velocity will remain in this state, provided that the particle is not subjected to unbalanced force. So from this law, we can basically state the law of inertia, which is a body in motion will stay in motion, and a body at rest will stay at rest unless acted upon by an external force. The second law, which is basically the fundamental law of dynamics, is that the particle acted upon by an unbalanced force experiences an acceleration that has the same direction as the force and a magnitude that is directly proportional to the force. The third law states that the mutual forces of action and reaction between two particles are equal, opposite, and collinear. So we can deduce the law of action and reaction, which states that for every action there is an action which is equal in magnitude but opposite in direction. In addition to the three laws, Newton also postulated the law of gravitational attraction, which is basically stating that any two particles or body will have mutually attractive gravitational force acting between them. This force is equal to G by m1 m2 over r squared, where F is the force of attraction between the two bodies, G is the universal constant, m1 and m2 are the masses of the body, and r is the distance between the center of the two bodies. Now, when we study the Newton's second law, we need to make a clear distinction between mass and weight, because the second law itself is dependent on the mass, m, F equals to ma. So the mass is basically an absolute property of the body. It is independent of the gravitational field in which it is measured. So the mass on Earth is the same as the mass on the moon, although the gravitational field on the Earth is different from the gravitational field on the moon. Basically, if we write down the second law as m equals to Fa, then we can read this law as mass provide the measure of the resistance of a body to change in velocity as defined by Newton's law. So mass is usually measured in kilogram or in pound depending on the unit system. On the other hand, the weight of the body is not absolute. It depends on the gravitational field in which it is measured. So weight is defined as W, which is the weight, is defined as mg. That's it. So it is the mass. The mass is the absolute property, but g is the gravitational acceleration, meter per second square. Now, g doesn't have to be 9.81 meter per second square, because this is the gravitational acceleration on Earth, but it can be anything else depending on where you measure it. The motion of a particle is governed by Newton's second law, and which is basically relating the unbalanced forces on the particle to its acceleration. If there are more than one force acting on the particle, basically we can write the equation as follows. So we sum up all of the forces. Forces are vectors, and basically we say that the sum of all of the forces equals to the one resultant force, which is going to be equivalent to m, which is the mass multiplied by the acceleration. Now in this slide, we are going to explain very important concept when we consider this simple Newton's second law, F equals to ma. And basically, if we have a particle P over here, okay, which is acted upon by two forces, F1, F2, as you see, they are vector acting in different direction, they have even different magnitudes. And we know that we just sum up the two vectors to get one resultant vector. So here we have one vector, another one, we sum them up to get the resultant vector right here. Now what the law is saying is that this left-hand side, which represent the sum of all forces. On the right-hand side, it says that this one is equal to m by a. The right-hand side gain its vector property from a, because a is an acceleration, it has a vector. But as you see, the law is very clear. The right-hand side has to have one single arrow pointing in the same direction as the resultant on the left-hand side. And I am sure that all of you know that the left-hand side is the famous, well-known free body diagram. But the right-hand side is the diagram that you are probably not familiar with. We call it the kinetic diagram because it basically shows kinetic property related to motion. That's why we call it kinetic property. Whenever we study the motion of bodies and the forces acting on them, we need to use what is known as the inertial reference frame or the Newtonian frame of reference. And basically, in a simple way, this frame of reference has to be either fixed, like here, this one is fixed, or even if it is moving, it has to be moving with a constant velocity. So it doesn't have any acceleration. And for that, we can measure the properties of particles using this frame of reference. The equation of motion can be extended to include systems of particles. This includes the motion of solids, liquids, or gas systems. So in this right side, the diagram we have an inertial frame here, and we have a system of particles. This system is acted upon by an external force Fi and an internal force Fi small, and we have, as you see, many particles. So if we consider the ith particles, okay, and we write down the equation of motion, Newton's second law, then the sum of all forces is supposed to be equals to the mass by the acceleration. So if I apply this law in the ith particle, then I will have Fi as a vector plus F small I, the internal force, also as a vector, is equal to mi, which is a scalar, multiplied by ai, which is a vector. Now, if we assume that the same equation right here was written for other particles, then we can basically say that the same equation will be obtained. And if we sum them up for all particles, we will end up with the sum of Fi plus the sum of small fi is supposed to be equals to the sum of mi ai as a vector. The next step is to note that the previous equation, which is fi, the sum of fi plus the sum of small fi equals to the sum of mi ai as a vector, that this equation, in this equation, the sum of the small fi has to be equals to 0, because the internal forces, if we sum them all, then they are going to balance. There will be 0, because internal forces between any two particles will occur in equal but opposite collinear pairs. And this is why this term will vanish. And we will end up with the sum of Fi equals to the sum of mi ai. Now, if we define Rg as a vector right here, which is pointing toward the center of mass, then by the definition of the center of mass, we can say that Mr G as a vector is supposed to be equals to the sum of mi ri as a vector, where m is equal to the sum of all masses, and basically it is the total mass. So if we differentiate this equation twice, we are going to get MAG, the differentiation is with time, so the differentiation of RG with time is VG, and you differentiate the VG with time, you get the AG, which is equals to the sum of MI AI. Now, clearly, if we look at this equation, and if we look at this one, we will get, if we substitute this equation into this, we will get the following. We will get the sum of the forces equals to MAG. This equation states the following. It states that the sum of the external forces acting on the system of particles is equal to the total mass of the particles times the acceleration of its center of mass g. So to summarize this session, we have introduced new terms like a gravitational force or gravitational acceleration or gravitational field. We have also talked about the mass, the weight, and the reactions. The mass is the measure of the resistance to change in velocity of the object. The weight is a force. It depends on the local gravitational field. The unbalanced forces causes the acceleration of the object. We also introduced the inertial frame, which is the frame that is either fixed or moving or translating with a constant velocity. And also, we introduced the kinetic diagram in addition to the known famous free body diagram. That's it. Thank you.